Now that we've had a chance to review quadratic equations, we're going to take a good look at quadratic functions and what their graphs look like. So the first thing we're going to do is define what quadratic functions are. We're going to determine what their graphs look like. And then we're going to show how to find the formula of a quadratic function by using 3 points on the graph. So first of all, a quadratic function doesn't look a whole lot different than a quadratic equation. The only difference is it's a function rather than something that's equal to 0. So a quadratic function has the form, at least its formula has the form, f of x equals ax squared plus bx plus c, where a, b, and c are constants. And of course, x is the input variable for the function. So as an example, g of x equals negative 2x squared plus 3x plus 5. That would be an example of a quadratic function. So let's go ahead and look at some of the graphs on Desmos so we can see what the graphs are going to look like. Alright, so here's Desmos, and what I want to show you in this particular part of the video is actually a nice way of looking at lots of graphs at the same time without having to retype them all in. So remember, we're looking at quadratic functions, so our functions look like f of x equals a times x squared plus b times x plus c. Now, of course, I haven't told you or Desmos, but for that matter, what a, b, and c are. But the nice thing we can do with this is we can add what's called a slider, which allows us to put in different values of a, b, and c. So I'm going to go ahead and do a, b, and c for my sliders. And then you can see we have these little dots here that we can move back and forth to give us different values of a, b, and c. And so what I want to do is I want to show you what the different values of a, b, and c do to the graph. So for instance, all three are starting at a, b, and c equal to 1, and I'm going to move a around. So I'm going to start at a equals 1 and make it a little bigger. So it shows you what the value is, 1, 2, 3, 4. And you can see, if you're looking at the graph, as a gets bigger and bigger, that the graph gets skinnier and skinnier. Now, if I move it back, back towards 0, the graph gets wider and wider. And as we get closer and closer to 0, it gets super wide, right? And then something weird happens at a equals 0. And then all of a sudden, the graph flips over. So at one point, we have this graph that opens up on both sides. And then when we flip to a being a negative number, all of a sudden it's looking down. And notice as it gets more negative, the graph gets skinnier again. There we have our graph. The other thing to notice is that the graph always either has a top when a is negative and a bottom when a is positive. And as I move the value of a, not only does the graph change shape, but that bottom and top of the graph sort of move around. Okay. Now let's look at what happens when we change the value of b. So once again, I'm going to start b at 1 and make it bigger and bigger. And notice that the graph moves around. But one thing you might notice about the graph, as I move it around, whether it's positive or negative, it doesn't even matter, the graph retains the same shape. I mean, we see different parts of the graph as the graph goes above and below, up and down, but the graph stays the same shape. Unlike with a, when we changed the value of a, it made the graph either skinnier or wider. So that was kind of interesting. And then finally, if I change c around, moving it up and down, again, the graph retains the same shape. But if you notice, actually, there's one thing I did want you to notice about the b as we moved it around. Just like with a, when we change the value of b, the bottom of the graph moves around. And it moves up and down and left and right depending on the value of b. And actually, that works even if a is a negative number. Let's show you here. Here the top of the graph moves up and down depending on the value of b. Now with c, the same thing happens. The top of the graph here moves in different ways, but notice that it doesn't move left or right. It only moves up or down. And again, that is going to be true whether or not A is positive or negative, whether the graph opens up or opens down. It's the exact same shape of the graph, just moves up and down when we change values of C. All right, so now we've had a chance to look at graphs on Desmos. Let's make some comments on what the graph looked like for different values of A and B and C. First, I want to note that for all values of A, B, and C, the graph is what's called a parabola, which means it has kind of a U shape, I guess you could say, either a U shape opening up or a U shape opening down. And the other thing that we sort of talked about was what the different roles that A, B, and C play in the graph. So if we think about what A does, it helps us, it determines actually a lot about the graph. First of all, it tells us whether the graph opens up or opens down. When A is positive, the graph opens up, and when A is negative, the graph opens down. But it also tells us how wide or narrow the graph is, when we have A being a large number. And when I say a large number, that's a large positive number, or a number that is very large but very negative. So 100 would be maybe a big number for A as a positive number, and negative 100 would be a big number. 1/2 would be a small number, and negative 1/2 would be a small number that's negative. So when A is large in size, the graph is narrow, but when A gets close to 0, and again, close to 0 either as a positive number or close to 0 as a negative number, the graph is going to be very wide. It also affects where the vertex of the graph is, and if you recall, not only it affects it in two different ways. It affects both where the x-coordinate of the vertex of the graph is and the y-coordinate. And by the vertex, what I mean is either the very top of the graph if it opens down, or the very bottom of the graph when it opens up. That part of the graph is going to change as A changes. And again, it'll change both vertically and horizontally. So that's a lot that A does. So let's think about what B does. First thing B does is it affects where the vertex is. And again, just like A, it affects both the x-coordinate and the y-coordinate of where that vertex is. Where the top of the graph is when the graph opens down, where the bottom of the graph is when the graph opens up. However, it does not affect the shape of the graph. Right? A affects the shape of the graph by making it wider or narrower, but the graph has the exact same shape when you change the values of B, no matter how you change it. It could be a positive number, it could be a negative number, it could be a big number, it could be a small number, doesn't matter. So let's think about what C does. C actually doesn't seem to do a whole lot, right? It determines where the vertex is, but only vertically. If I change the value of C, it only moves the graph up and down. It can't move the graph to the left or to the right. It does not affect the shape of the graph at all. Just like B doesn't affect the shape of the graph, C also does not affect the shape of the graph. So in fact, the only one of those constants that does affect the shape of the graph is the value of A. And of course, it does not affect the x-coordinate of your vertex, only the y-coordinate. All right, so those are some observations on what the graph of the function looks like. So now what I want to talk about is what kind of information you have to have in order to find the equation of a quadratic function. Remember back in the old days, if you wanted to find the equation of a line, well, there are actually two ways that you can have information to figure out the equation of a line. You could either have a point and a slope, or you could just have 2 points. But in any case, you need 2 points to figure out the equation of a line. 1 point by itself will not determine a point on a line. And so the question you might ask is, how many points do you need to determine a quadratic function? Well, it turns out you need 3. So 2 points for a line, 3 points for a quadratic function. And I'll show you how to do that in this example. So suppose you have a quadratic function, and if you look at the graph, the only thing you know about the graph is you have these 3 points, 1, 0, 2, 1, and 3, 6. So we know we have a quadratic function, so it's going to look like a times x squared plus b times x plus c, and we need to figure out what a, b, and c are. And what we're going to do is we're going to plug those points in from the graph into the function to see what kind of information it gives us. Now, one thing I want to remind you about those points on the graph is they tell us not just what the graph looks like, but also what three of the inputs give you as outputs. It tells you that if you put in x equals 1, you get f of x equals 0. If you put in x equals 2, you get f of x equals 1. And if you put in x equals 3, you get f of x equals 6. And that actually gives you some really important information. So for instance, if we plug in x equals 1, well, we can think of that in two ways. First of all, we can plug that x equals 1 into our formula, ax squared plus bx plus c, to get a times 1 squared plus b times 1 plus c. And if we simplify that a bit, we get a plus c. But also, if we look at that first point that's on the graph, 1, 0, that tells us that if x equals 1, f of x equals 0. So that tells us that f of 1 equals 0. So that gives us two pieces of information about f of 1. And if we look at that second point, 2, 1, we can do the same thing with x equals 2. We can plug that into the formula to get a times 2 squared plus b times 2 plus c. We can simplify that to get 4a plus 2b plus c. But then we can also plug it into the point f of 2 is equal to 1 because the x-coordinate is 2, the y-coordinate is 1. We can do the same thing with the third point, f of 3 equals 6, but also f of 3 is equal to, using the formula, a times 3 squared plus b times 3 plus c. We'll simplify that to 9a plus 3b plus c. And then we can also plug in the point f of 3 equals 6. So now let's go ahead and clean those up. We really just have three nice equations. I'm sorry. That first line says that f of 1 is equal to a plus b plus c. It also says that f of 1 equals 0. Both of those f of 1s are the same number, which means that a plus b plus c and 0 have to be equal. So we get a plus b plus c equals 0. So we get a nice little equation. We can do the same thing with f of 2. f of 2 is equal to 4a plus 2b plus c. It is also equal to 1, and that tells us that 4a plus 2b plus c is equal to 1. And the same thing with f of 3, that is equal to both 9a plus 3b plus c, and it's also equal to 6, so we can set those equal. And now we have a system of equations, three equations, three unknowns that we have to solve for, so we can use all those techniques for solving systems of equations on this one. And I'll show you how we do it here. It's very similar when you do them on other ones as well. So probably the most straightforward way is to solve for one of the variables in one of the equation in terms of the other. So I'm going to look at that first equation and solve for c. So I'm going to solve that system of equations. I'm going to take that first equation and solve for c. That's just subtracting a and b from both sides. So we get c equals minus a minus b. Now that c in the first equation is exactly the same as the c in the second and third equation. So I'm going to substitute c equals minus a minus b in for the other c's in those equations. So there we go. That 4a plus 2b plus c becomes 4a plus 2b plus negative a minus b. And similarly, 9a plus 3b plus c turns into 9a plus 3b minus a minus b. And we can simplify those, right? 4a minus a is 3, 2b minus b is b. And we can do this similar thing with the third equation, just clean those up. We end up with 3a plus b is equal to 1, and then 8a plus 2b is equal to 6, which is nice. Now we've just gotten those two equations down to two variables. We can play the same game with those two equations as well. We can solve for b in that second equation to get subtracting 3a from both sides to get b is equal to 1 minus 3a. We can take that b, substitute it for the b in the other equations. Both the top equation, we had minus a minus b, turn that into minus a minus 1 minus 3a. And similarly, we can plug in b equals 1 minus 3a into that third equation. And that's what we get. Now, of course, we can simplify those as well. That minus 1 minus 3a, that negative can distribute to give us negative a plus negative 1 plus 3a. And then when we solve that one, or when we simplify that one, we get c equals 2a minus 1. We can do the same sort of thing with the third equation. Multiply that 2 through to get 2 minus 6a. Combine that minus 6a with the 8a to get 2a. And then, whoops. Oh, yeah. We also going to subtract 2 from both sides. Do a little bit of simplification. We get 2a equals 4. and then divide both sides by 2 to get a equals 2. So that's just doing a little bit of algebra, but now that a equals 2 can be substituted in for all the other a's. So we can substitute it in for 2a minus 1 to give us 2 times 2 minus 1, and we can substitute it in for 1 minus 3a, that gives us 1 minus 3 times 2. And then we solve for those. We get c equals 3, b equals negative 5, a equals 2. We found all of our constants. Now we can just plug those into our function. When we plug in a equals 2, we get 2x squared. b equals negative 5 gives us a negative 5x. And c equals 3 gives us a plus 3. So we get 2x squared minus 5x plus 3. All right, so hopefully that gives you an idea about how to deal with quadratic functions. Now is a good time for you to look at those activities. They're called Introduction to Quadratic Functions, and they're included with this video on a PDF file.